Picture a skydiver stepping out of a plane. For the first few seconds, she speeds up fast, gravity pulling her down harder and harder. But keep watching, and something strange happens. Her speed stops increasing. She's still falling, gravity hasn't switched off, yet she settles into a steady rate. What's actually going on there? By the end of this lesson, you'll be able to explain it properly. You already have a working idea of speed from everyday life. It's simply how much ground something covers in how much time. A car that's fast covers a lot of distance quickly. Something slow takes ages to get anywhere. That everyday sense is exactly the seed we're going to grow into a precise physics tool. Imagine two runners covering the exact same 100-meter track. One finishes in 12 seconds, the other in 15 seconds. Which one was moving faster? The one who took less time, of course, because they covered that same distance more quickly. Notice what changed here. The distance stayed fixed, but the time taken decided who was faster. Let's turn that observation into a formal equation. Speed, v, equals distance traveled, s, divided by time taken, t. So v equals s over t. Here, s is measured in meters, t in seconds, and v comes out in meters per second. If you cover 20 meters in 4 seconds, your speed is 20 divided by 4, which is 5 meters per second. Speed alone tells you how fast something moves, but it says nothing about which way it's headed. Velocity fixes that gap. Velocity is speed in a given direction. So a car might have a speed of 60 kilometers per hour, but its velocity is 60 kilometers per hour due north. The number is the same. The extra piece of information is direction. It's tempting to treat speed and velocity as just two names for the same thing. Test that idea. Imagine two cars, both traveling at 50 kilometers per hour, one heading east and one heading west. Same speed, clearly. But their velocities are different because velocity cares about direction, and these two are moving opposite ways. Speed ignores direction. Velocity depends on it. Real journeys rarely happen at one constant speed the whole way through. You might sprint for a bit, then slow to a jog. To describe the whole trip with a single number, physicists use average speed, calculated as total distance traveled divided by total time taken. It smooths out all the speeding up and slowing down into one overall figure. Try this. A cyclist rides 300 meters in 60 seconds, then a further 200 meters in 40 seconds. What's her average speed for the whole ride? Add the distances. 300 plus 200 gives 500 meters. Add the times. 60 plus 40 gives 100 seconds. Divide. 500 meters over 100 seconds equals 5 meters per second. That's her average speed, even though her actual speed varied along the way. Now look at motion drawn as a graph, with distance on the vertical axis and time on the horizontal axis. If the line is flat, distance isn't changing while time ticks on, so the object is at rest. If the line is straight but sloped upward, distance is increasing steadily as time passes, which means the object is moving at constant speed. Here's the key link between the picture and the number. The steepness of a straight section on a distance time graph, its gradient, is exactly equal to the speed of the object. A steeper line means a bigger change in distance for the same change in time, which means a higher speed. Read the slope, and you're reading the speed. Suppose a straight section of a distance time graph passes through 10 meters at 2 seconds and 40 meters at 10 seconds. What speed does that represent? Find the change in distance. 40 minus 10 is 30 meters. Find the change in time. 10 minus 2 is 8 seconds. Divide 30 by 8, and you get about 3.75 meters per second. Here's a prediction for you. What do you think it means if the line on a distance time graph curves instead of staying straight? A curve means the gradient itself is changing from moment to moment, which means the speed isn't staying constant. The object is either speeding up or slowing down somewhere along that curve. That changing speed deserves its own quantity, acceleration, the rate at which velocity itself changes. We write it as A equals delta V over delta t, where delta V is the change in velocity and delta t is the time taken for that change to happen. Acceleration is measured in meters per second squared, telling you how many meters per second the velocity changes every single second. Now switch to a speed time graph, with speed on the vertical axis instead of distance. A flat line here means the speed itself isn't changing, so the object moves at constant speed. A straight sloped line means the speed is changing steadily, which is constant acceleration. And a curved line means the acceleration is itself changing from moment to moment. Just as gradient on a distance time graph gave you speed, gradient on a speed time graph gives you acceleration. A steep slope means speed is changing quickly, a large acceleration. A gentle slope means speed is changing slowly, a small acceleration. Same trick, new graph, new quantity. Students sometimes treat deceleration as some separate, opposite quantity to acceleration. It isn't. A deceleration is simply a negative acceleration, a slowing down described using a minus sign inside the very same equation. There's no second formula to learn, just a sign that tells you the velocity is decreasing rather than increasing. A car's speed falls from 20 meters per second to 5 meters per second over 5 seconds. What's its acceleration? Change in velocity is 5 minus 20, giving negative 15 meters per second. Divide by the time, 5 seconds, and you get negative 3 meters per second squared. The negative sign confirms it's decelerating, exactly as we'd expect from a car slowing down. There's one more powerful reading of a speed time graph. The area enclosed between the line and the time axis equals the distance traveled. This works whether the object moves at constant speed, giving a simple rectangle, or accelerates steadily, giving a triangle or a trapezium shape. Area under the graph is distance. Full stop. Consider a runner holding a steady 10 meters per second for 4 seconds, then accelerating up to a faster speed over the next 4 seconds, forming a triangle on top. The rectangle gives 10 times 4, which is 40 meters. The triangle on top gives 1/2 times 4 times 10, which is 20 meters. Add them together, and the total distance covered is 60 meters. Near the surface of the Earth, any object falling freely speeds up at a rate that's approximately constant, called the acceleration of free fall, g. Its value is approximately 9.8 meters per second squared. That means every second an object falls without resistance, its downward speed increases by about 9.8 meters per second. Now, return to our skydiver. Right after jumping, air resistance is small, so gravity dominates, and she accelerates close to g. As her speed builds, air resistance grows too, pushing back against her fall and shrinking her acceleration. Eventually, air resistance grows large enough to balance gravity completely. Acceleration drops to 0, and she falls at a steady, unchanging speed, called terminal velocity. Quick check before we move on. On a distance time graph, what does a flat line mean? And what does a straight sloped line mean? Now switch to a speed time graph. What does a flat line mean there, and what does a straight sloped line mean there instead? The shapes look similar, but they're telling you about different quantities. Here's a fresh scenario to test your whole toolkit. A cyclist's speed time graph shows speed rising steadily from 0 to 8 meters per second over the first 4 seconds, then holding at 8 meters per second for the next 6 seconds. Find her acceleration during the first phase using the gradient, then find the total distance covered across both phases using the areas. Work it through before checking your reasoning against everything you've just learned about gradients and areas. Step back and see how it all connects. Speed and velocity describe how fast something moves, and for velocity, in which direction. Acceleration describes how that velocity itself is changing, including the negative case of deceleration. Distance time graphs reveal speed through their gradient, while speed time graphs reveal acceleration through their gradient and distance through their area. Free fall with air resistance ties it all together, showing acceleration shrinking to 0 at terminal velocity. Whenever you meet a new graph or a new falling object, ask yourself, is this quantity changing? And what does that graph's slope or area actually represent?